One of the big questions in modern physics is how do we know what stuff is made of? Like, for example, how do we know whether light is a wave or a particle? Well, one of the ways you can test for whether something, be it light, electrons, protons, whatever, is a wave or a particle, is with what's called a double slit experiment, because a double slit is going to create very different behavior based on whether the thing that's coming in is a particle or a wave. Let me show you what this means. Let's suppose you send a wave into this experiment. Maybe you turn on a laser so that the wave is nice and everything's in sync, right? Everybody does max and min at the same time. When the wave hits this wall here, it's going to get blocked. Well, most of it's going to get blocked. One small piece of it is going to get to come through this hole, and one small piece of it's going to get to come through this hole. So it's like you have two wave sources that are still oscillating in sync with each other. So in other words, I'm going to get a wave coming out of here and a wave coming out of here. And because they're coming out of this point source, really, really small, really narrow slit, they're going to proceed out in spheres, right? Because it's got to spread out in all directions. Here, as a plane wave, it's spreading out in the one direction because as each point spreads out, those circular spreads are canceling and reinforcing this plane wave nature. So you have a plane wave turning into two spherical waves. What that's going to do, you know what waves do by now. You know that they interfere with each other. So wherever you have two peaks meeting, so the red lines here represent peaks, you're going to end up with a bright spot, meaning that's where the light, the wave, whatever it is going to be brightest. It's going to be at its highest magnitude. Wherever you have a peak meeting a trough, so like for example here, you're going to get a dark spot. So see here, you're in between two waves from this source, you're at a maximum on this source, as that means it's going to be a dark spot. You're not going to see anything there. It's going to be dark whenever you put a screen in front of it. You let that continue on along here to the screen on the other side, and watch where the two waves light up. So you'll end up with a pattern, right? Because you're going to have a bright spot here, and you'll end up with a dark spot here. You'll end up with another bright here, another dark here, another bright here, another dark here, and then it repeats down this way. A dark, a bright, a dark, a bright, a dark, a bright. And so if you shine your source, if you send stuff at the double slit and you get this pattern of bright, dark, bright, dark, bright, dark, the thing must have been a wave. Now compare that with sending particles. Let's suppose you send a shower of particles at this screen, right? Most of them are going to get knocked back by the wall, but a few of them are going to get to come through. Well, if I'm a particle up here, I don't really care about particles down here coming through. So I'm just going to continue along my merry way. And I'm going to end up with a lot of particles here. And I'm going to end up with a lot of particles here. Right? So if you send your stuff at the double slit and you get a cluster of hits here, and you get a cluster of hits here, and you get basically nothing anywhere else, then this thing that you sent through must have been a particle. Let's take a look at a glow script simulation that will show.
So here's a code to demonstrate the double slit experiment we just talked about. First, we're going to set the wavelength of our light coming through, and we're going to create two sources for the light. These are each going to be a sphere located down on the screen. So notice they're both at y equals -3, so they're going to be farther down on the screen. We're then going to set up some points on a grid. Let me show you what this means. We're going to create a list called vertices. So the way you create a list in Python, or one way, is to just create an empty list with open bracket, close bracket. That means I want a list, but I haven't added anything to it yet. Then we're going to make two loops. We're going to loop over the x values. We're going to loop over the y values so that we go to every point in the grid. At each one of those points, we're going to create a box. The box is going to be at the points x and y that we're looping over, and we're going to give it a really small size dx. We're then going to calculate what's called the path difference. This is the difference you would get if you traveled from source number 1 to the point you're at, and from source number 2 to the point you're at, because that's the thing that determines whether you get a bright spot or a dark spot. So you can see we're taking the distance from the square we're at to source 1 and the distance between the square we're at and source number 2. Here what we're doing, we're taking what's called the modulus between the path difference and the wavelength, because if the path difference is an integer multiple of the wavelength, then this modulus will be close to 0. But if it's separated by half a wavelength, then this modulus will be close to a half. Where that's important is we're going to code that into the brightness of this particular spot. So if we're at a half, if we're half a wavelength off, then this brightness is going to be 0. We're going to take 1/2 minus a half, give us 0. On the other hand, if we are an integer number wavelength apart, if this n is close to 0, then this will be 0.5 divided by 0.5 will give me a brightness of 1. So we're going from 0 to 1. So this brightness has to come between 0 and 1, because this n is always going to be somewhere between 0 and 1, and we're taking that number minus a half and dividing it by a half. So we're making up a number combination that will give us something between 0 and 1 to scale whether we're at a bright spot or a dark spot. Here we set this particular square's color. The color is going to be red, and it's going to be scaled in terms of red based on the brightness. So a brightness of 1 is going to be very, very red, and a brightness of 0 is going to be very, very not red. And in fact, a color of 0, 0, 0 is going to be black. It's going to be a dark spot. Then we just add that to our list of vertices, our list of squares that we're looking at on the grid. So this is the half of the code that gives us the wave half of the double slit experiment. Then we're going to do the particle half. We're going to start shooting particles from those two sources. So again, we make a list. This is now a list of particles. And we're going to loop over until we've created 500 particles. That's what this len means. It means how many particles are in the list of particles. If that number is less than 500, keep going. Let's see, here we pick a random number. Random numbers are incredibly useful in code when you want something to happen at random, basically. If you're not looking for something to happen constantly, if you're just looking for something to happen with some kind of variation, you just pick a random number. In particular, this random number function always picks a number between 0 and 1. So it's any decimal value between 0 and 1. So here we're looking at if the random number is bigger than 0.9. So there is a 90% chance that it is smaller than 0.9, and there is a 10% chance that it is bigger than 0.9. So basically, we're looking here at a 10% chance. So 1 out of every 10 frames, 10 out of every 100 animation frames, we're going to add a new particle. So we're taking the list of particles and we're using this append function. Append just means take this new thing that I'm making and add it onto the list of particles. So we create a sphere here. We give it a position at source 1. We give it a color white so that we can see it against the red background. And we give it a velocity. Now here's the cool part. We are also randomizing the velocity. Right? Each time you call this random function, it's going to give you a different number between 0 and 1. So we give it a random velocity in the x direction and a random velocity in the y direction. So we give it a random velocity in the x direction, a random velocity in the z direction, and a definite velocity of 1 in the y direction because we want it to travel across the double slit field. We don't want it taking its sweet time getting there. Then we do the same thing for source 2. We pick another random number. Each time you call random, it's a different number. And again, there is a 10% chance here of firing a particle from source number 2. So everything else about this line is the same about this line. The only difference is we're coming from source number 2 instead. Now we are firing those particles. We want them to move, right? We gave them a velocity, but we have to actually tell them to move. So what we're going to do here, we're going to loop over all the particles we have. If we haven't created any particles yet, it'll just skip this part. But this is saying for each p, for each particle in particles, for each individual particle you have, we're going to update its velocity. Hey, look, it's that update equation. That thing must be pretty important. Again, this is just a rearranged version of velocity equals delta x over delta t, where you're saying I want the change in x based on my velocity times the time step. Again, this delta t, this is just a small number. It's a small step forward in time, so that now I can say my new x is equal to my old x plus v times delta t. In other words, you're taking x and you're adding to it v times delta t. These two equations mean the exact same thing. This one means take the old, add the change, get the new. This one means take the old and add to it the change, v times delta t. That's exactly what you have here in this equation. Position plus equals velocity times t. That's all it means. We need it to stop when we reach the top of the screen. So if our y position is greater than or equal to our top value, then we're going to set the velocity to 0. So a great way to get something to stop moving is to set the velocity to 0, because then up here when I go to add this to the position, it's just going to be a 0 by default. All right, let's press Control 2 to run this and see what we get. Here you get the interference pattern from the light waves coming out. I can even right click and drag this thing. You notice that I get a line of bright spots here, a line of bright spots here, a line of bright spots here, and so I get my bright patches on the screen here. Meanwhile, I'm firing particles out of these sources. You notice they've got a little bit of spread to their x and z velocities while they're continuing along the y direction just fine. And so I've got this collection of particles here, collection of particles here. This confirms what we saw on the board, that if I'm shooting particles through a double slit, I should expect to get a cluster here and a cluster here and no particles anywhere else. But if I'm shooting a wave through the double slit, these are the two slits here, then I expect to get this lovely interference pattern here, and I expect to get bright band, dark band, bright band, dark band, bright band, dark band. You can even extend this if you wanted to. You can make this thing broader. Let's go back to our code. All you have to do is change this X max here. So for example, suppose I change my X max to 4 and I let that wall go out a little bit farther. I can see a little bit more of the pattern over here. I could even just extend the wall in the X direction. So let's suppose I multiply these by 2, get myself more along the X direction there. Yeah, you can see more of the pattern now where I've got these 3 nice bright bands. I got dark bands over there. You can expect another bright band somewhere farther out over there. You can also change the wavelength. So let's suppose I make this wave much shorter. Let's suppose I decrease the wavelength by a factor of 10 and rerun the code. Now you notice my bright spots are much closer together. Oh, actually, my mistake here is I need to make dx smaller. So if your dx is on the order of your wavelength, it's going to basically wash out there. Think of this dx, think of that as kind of the resolution of the picture. So think of it as the size of the pixel. There we go. That's better. Now you get a better idea of having these bright spot here, bright spot, bright spot. So this is really showing you what that interference pattern looks like. And then of course we have our particles shooting out here. You notice the particles obviously not affected by the wavelength because they're not waves, at least they're not supposed to be. So you can play around with this, get an idea of how this double slit experiment works, what kind of stuff you can expect to get there based on whether you're looking at a particle or whether you're looking at a wave.